All right, hey gang. First air test review of the year in preparation for the big day next week. Hey, let's do our best, guys. You guys all know how to do every problem on this test. Some of the questions are worded weirdly, so you have to really think through what they're asking, but you know everything. And so I'm excited for what you guys can do moving forward in this test. So let's get after it. Pay close attention to how I go over things, how I read things, interpret things, break down the questions that they're asking, and then refer back to what we've already known to be true, which is the concepts we've studied this year. So let's get after it and see what we can do. All right, so in taking a look at the very first one, it says this. We're going to work on similarity and trigonometry. Now, similarity, here's what I'm thinking. Ways to prove triangles similar. Angle similarity, side angle side similarity, and side similarity. What do we know about similar polygons? All of their corresponding sides are proportional and corresponding angles are congruent. So please remember those. Those 5 things I just rattled off there? They are super important when talking about similarity. Corresponding sides are proportional, corresponding angles are congruent. Trig, I'm thinking sine, cosine, tangent. And so, yeah, just SOHCAHTOA. Make sure you know how to work the trig functions there. Also, don't forget, make sure that your calculators are in degree mode, correct? Degree mode, okay? So the very first one says, a park has a triangular sandbox. Todd wants to create a smaller sandbox at his backyard having the same angles as the park sandbox. Drawing of both sandboxes are shown. What is the perimeter in feet of Todd's sandbox? Okay. So here's what I'm thinking. There's several different ways to address this here, but one thing we could do is figure out the scale factor of the larger triangle to the smaller triangle. Okay. Now, if we do that, we're getting smaller here. I wrote down 8/20ths. You could also do, what would that be, 2/5. You could do 0.4 or 40%. All of these would be correct, the scale factor of what we're looking at. Now, if I take maybe 0.4 for the time being, if it isn't a nice clean decimal, you would want to use the fraction. But if I go ahead and do one of two things to find this length right here, I'll just say it's x for right now. I could set up a proportion like this, 2:5, as 8 is to, 2:5. 2:5 as x is to 14. Let's change that. Make that x is to 14. Okay. You could also say 8 is to 20 as x is to 14 would also work. Another way to do this problem right here, well, actually, let's just finish this up. If I cross multiply here, I get 5x equals 28. And if I divide through by 5, you get 5.6, okay, or 5 3/5. Now, you could have done the same thing if you would have taken this 0.4 and multiplied it by 14, because this length here, remember, is 40% of that length right there. So in your calculator, if you take 14 times 0.4, I'm pretty sure you're going to get that 5.6, okay? In fact, I may do that same thing for the y value over here. You can set up your proportion again. Maybe I'll use 8/20 this time equals y over 18. And now this will be the exact same thing as taking 18 and multiplying that by 0.4, okay? Now, either way, you're going to get 7.2 for the length of y, okay? Which is good. It's longer than x, we know that. It's also less than 8 because 8 corresponds with the longest side from the other triangle. Now, it's super important that we identify what we're looking for. We're trying to find the perimeter in feet, okay? Make sure that there's no conversions that need to be made. These are all in feet. Now I can find my perimeter. If I just go ahead and add up each of the side lengths, 5.6, 7.2, and 8, that will give me 20.8 feet for my perimeter. And so that right there is my perimeter of that smaller sign box, okay? All right, now, the next one, I'm going to kind of scoop this under here, says this: a company wants to design a cylindrical object that has a height of 10 centimeters and a volume of at least 2,000 cubic centimeters, but not more than 2,500 cubic centimeters. What is a possible radius in centimeters? Now, what that tells me, folks, is that there's a range of possibilities that we could use here, okay? And we just have to kind of figure out what that range is of the cylinder. Round your answer to the nearest hundredths place. Now, on my test, I might even highlight this part. Hundredths place, remember, means this: 2 places after the decimal, okay? So don't forget that, 2 places after the decimal, nearest hundredths place. So let's go back here. The volume formula for a cylinder is definitely something that I would have memorized. It is not going to be on your formula sheet. There is a formula sheet embedded both in the testing interface on your computer, but also we're going to give you that formula sheet as a hard copy that you can see. But this formula is not part of that formula sheet, okay? And so if you remember, volume of a prism is base area times height. Well, the cylinder has the same formula, and the base area is always the circle, so area of the circle times the height is your volume of your cylinder formula. Now from here, remember our answer has to be between 2,000 right here and 2,500 over there, 2,500 cubic centimeters. So what I'm going to do is this: we don't know what the radius length is, but we do know what the height is going to be. It's a 10 centimeters. That was given to us also in the description there. So our answer has to be between 2,000 and 2,500. Okay? Now, obviously, you can go ahead and use guess and check here with this. In fact, I think you can even plug it into Desmos, and I may check that here in just a second. I wish there was a way to pause my, probably can, but check it in just a second. But here's how you can solve this algebraically. If you divide everything by 10 pi, pi's cancel out, 10's cancel out, everything by 10 pi. Now remember, keep it in parentheses here. In fact, what I would probably do, if I divide by 10, I can get rid of a 0 here. So now we have 200 divided by pi and 250 divided by pi. And that is going to be for the radius squared. Okay? And if you go ahead and square root everything, that gets rid of the squared part, and that'll be the radius length. Okay? So now, if I go ahead and, let's see here, round to the nearest tenths place. If I go ahead and work that out in my calculator, which I don't have right here, what you're going to find out, and I'd encourage you to plug that in your calculator, is that the radius length should be between 7.979 and 8.921, I believe. Okay, now that's without me plugging into the calculator there, but that would be, a range. So therefore, you should be able to plug in maybe 8.00, the nearest hundredths place. Okay, 7.99 would also work. Okay, it's in that range. 8.50 would be a possibility there. But anything in that range is what you're looking for. Now, if I could go back for a moment, if you said, hey, that whole algebra thing threw me for a loop, here's what I'll tell you. If you plug this into Desmos right here, I'm going to tell you right now, it'll give you the answers. Okay? In fact, I may do that right now just so you can see it. And as I pull this up, I'm going to show my computer here. Let me make sure I'm showing my computer right. There we go. I'm going to show this and actually look through this with you. Get rid of that. Here we go, graphing calculator. Let's see if this works here. 2,000 less than or equal to, let's go actually back here. And then I have pi radius squared times 10. I'll just put the 10 out front. Pi, and I'll put x squared. And I want to go less than or equal to 2,500. Does it work? It doesn't. I wonder why. We're only supposed to be solved double inequalities. Try deleting one side of the inequalities. Okay. So, could do this. Okay, nice. There's that. And then I could do the opposite. 2,000. And watch what happens. Oh, let's copy that. Control C, Control V. Oh, nice. Okay, now we'll go back home. Now, if we look here, now we don't be the negatives there. Okay, there's the one side. Okay, and here's the other. 8.921. So yeah, there's that range there that we can actually. That overlap is what we're looking for, guys. So yeah, that's beautiful. That's really nice. So. Hopefully that makes sense to everybody. All right, now, in looking at the next one, Desmos cheat code on the ear test, that's right. Taking a look at this next one, it says this. Felicia wants to draw a triangle, of course she does, PQR such that the conditions are shown to be true. The area of triangle PQR is not, now make sure you highlight that because it's not 6 square units. We're going to come back to that in a second. Remember the area of a triangle formula, okay, hopefully I'll have this down by now, is going to be 1/2 the base times the height. Okay, so don't forget that. And then it says such that the cosine of P is 0.6. Now what does that mean? Well, first of all, let's explain a little bit more about what the cosine of anything means. Cosine of theta, well, what does that mean? It means the adjacent over the hypotenuse. Okay, so now as I think about that, it says the cosine of P is 0.6. Well, what does that mean? Well, if you know anything about 0.6, you could put that this is 6/10, 6/10. Okay, so I'm thinking that we could do something like this. I think we could make this a length of 6, and this a length of 10. Okay, and I'll make this P, adjacent over hypotenuse. Okay. Now remember, with trig functions, you have to have a right triangle. All right. Now, how do we figure out what this other length is going to be? Because we want to make sure, again, going back to the directions here, that our area is not 6 square units. Okay. So as I look here, I'm going to go ahead and say this: 6 squared plus b squared equals 10 squared. That'd be one way to do it. If we work it out, 36 plus b squared equals 100. B squared will equal 64, and b will equal 8. Okay. Now, if you notice, this is actually a 3, 4, 5 right triangle. I almost started with this up here being 3/5 because 0.6 is 3/5. But look at what happens if I would have made it 3/5. If I would have used 3/5 here, this would be 3, 4, and 5. What's the area of this triangle? Well, your base right here is 3. The height is 4. 3 times 4 is 12. Half of 12 is 6. the area would be 6 square units. What did it say up above? So that it's not 6 square units. So this right here, the area would be 6 times 8, which is 48. Half of that is 24. So therefore, the area of this triangle is 24 square units. So if I go back to finish this up, it says use the connect line tool to draw one possible triangle PQR. Then drag the letters and vertices to label each triangle. So it'll be important as you work this out. I'm going to label it right here. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6, 7, 8. And I'm going to put P right here so that the adjacent to hypotenuse is that 6/10. Okay. Now, I don't think, yeah, it doesn't matter where you put Q and R. I may put R here. I can put Q here. You can switch those. That's not the important part, but P has to be here to have the adjacent to hypotenuse be 6/10 or 0.6. Okay? So now you may be asking yourself, is this the only triangle I could put out here? And the answer is no. You could double each of these sides. It could be 12 to 16 to 20. Okay? The key was that you couldn't use that 3, 4, 5 right triangle because it would have given you an area of 6 square units there. Okay? So again, if they give you a decimal for a trig value, just think a little bit deeper about what that means. And in this case, adjacent to hypotenuse and also 6/10. Okay? So hopefully that makes sense to you there. All right, now the next one says this. Let's see here. The equation of a line is shown. If I can get up here a little bit higher. The equation of a line is shown 6x minus 3y equals 5. A dilation centered at the origin with the scale factor of 6 is applied to the line. What is the slope of the line after the dilation? What is the value of the y-intercept of the line after the dilation? Okay. Now, there's a couple of things that I want to think through here. First of all, if you're not sure how to graph this line, plug that into Desmos. Okay. In fact, I'm going to show that here real quick. If I go ahead and show what that would look like, let's go to Desmos here. And again, 6x minus 3y equals 5. Okay. And I would make sure, okay, I've got that. That makes it difficult because it's not a whole number. That makes it difficult because it's not a whole number. But what I could do with this so that I can figure out the whole number, oh shoot, I can't. I was hoping to go ahead and just use the table function. So going away from that then, if we come back here, what we can do is remember change this standard form equation into slope-intercept form. And what I mean by that is this. If this is my original equation, how do I get y by itself? Well, in the first step, I would subtract 6x from both sides. And then I would divide everything by negative 3. If you divide this by negative 3, it gives you a positive 2. Divide this by negative 3, it gives you a negative 1 2/3. Okay? Now, if you remember, we did see that on our graph there. If we go back to Desmos here, okay, hopefully you can see that okay. Let me check it real quick. Oh, maybe a little bit higher. There we go. Okay. If you look here, negative 1 2/3 is what we're looking at right here. So one way to double check this would be to plug in this other equation, y equals 2x minus 1 2/3. 1 2/3. And I'll go here just to make sure. Oh, come on now. Divide that out. 3. Oh, 3. And if you look, I'm trying to get this to come. There we go. Okay. You'll notice that these two equations are the same equations. Okay. Now watch this. One thing you could do is use your table function. You see what I did there? Gear shows you a table function, and you could actually find some whole numbers, I'm pretty sure. Maybe not. I would have thought that it would have given you a whole number to place it on. Anyways, if I go ahead and find what is the slope of a line after the dilation, let's go back to our paper here. Okay, and in order to figure out the slope, I'm going to do this. Let's see here, -1 2/3. I'm going to try to place that point right there. And has a 2 slope, so, oh, well, shoot, 1 2/3 should be here. There we go. So if I go up 2, 1, 2 over 1. 1, 1, 2 over 1. 1, 2 over 1. Okay, so this is my line right here, and I'm going to try to graph that line real quick. Okay, didn't do great at it, but you know, good enough. All right, now here's what I'm going to do. You notice I've created a kind of a triangle right here. So there are two things that we need to remember about similar polygons, because we are dilating this figure at a scale factor of 6, it says here. So I'm going to take this triangle here, and this angle down here right there, that angle is not going to change no matter how big or small I get my figure to be, because this triangle, a similar figure, if I dilate it, is going to have the same angle. So here's what I'm going to say. What is the slope? Get up a little bit. What is the slope of the line after the dilation? It's still going to be 2. Okay, that angle won't change with that triangle that I just formed, that line right there. That angle will not change no matter how big or small that line gets, okay, from that point. Now the second part is, what's the value of the y-intercept of the line after the dilation, okay? So we know this y-intercept, as we said before, was what? -1 2/3. So I'm going to go ahead and multiply that value by 6, okay? Remember, when we dilate something, if it gets bigger, it's going to get further from the center of dilation. In this case, I'm going to make my center of dilation the origin, okay? So as I do that, -1 2/3. I would encourage you to use Desmos when you do that. It's a simple, you plug it in, you can see things really well. But if I do that, you end up getting a negative, let me think here for a second, 6, 12, so it'll be 4, so a -10, okay? So this, to put it in perspective, this point is now 6 times as far from the center of dilation, the origin, than it was originally. So that would go all the way down there to -10. So I'm going to say right here, with a scale factor of 6, that point is going to be at -10, okay? All right, now let's move on to our beloved proofs. Let's see how we can do here. I'm going to try to walk you through the proof, show you what you can do here. Let's see here. Okay, all right. So it says up here at the top, it says, Mark is proving the Pythagorean theorem. He draws right triangle JKL with an altitude of JM. An altitude, remember, is a line that's perpendicular. So this is the altitude right here. Perpendicular to a side, the height of the figure, basically. First, he proves the triangles JKL, and MKJ are similar. Then he proves triangle JKL and MJL are similar using the angle-angle criterion. Angle-angle similarity is what we called it. They call it criterion. Okay, same thing. The rest of his proof is shown with some steps missing. Okay. So it says here that the triangles are all similar. They've already proven that, I guess. And now he says JK is to LK. JK is to LK. So in this big triangle, the short leg is to the long leg, as MK is to let's see here, MK is to JK. Let's see. JK is to LK. Oh, that's why I misread it here. So they're doing short leg is to hypotenuse in this big triangle. So we've got a short leg, a long leg, and a hypotenuse. So they did short leg is to hypotenuse as short leg is to hypotenuse. So that just showing that the corresponding sides are proportional of similar triangles. In the other pair of similar triangles, they did LJ is to LK. So long leg is to hypotenuse as ML, long leg is to hypotenuse JL, okay, or LJ. Now from here, what they did was they cross multiplied. JK times JK is JK squared. LJ times LJ is LJ squared, okay? Now what they're going to do next, and the answer is A right here. And let me explain why A is the answer. If I write this in, okay, scoot that up, there we go, to our figure, what they're doing is they're adding these two portions together and therefore adding these two portions together. And if you add the same thing to both sides of an equation, okay, they aren't any bigger since they're equal, they have to maintain equality. So again, JK squared plus LJ squared will equal LK times MK plus LK times ML, all right? And again, that's the addition property of equality. And that takes us back a long time, okay? Back to the beginning of the year, right? Now, the next thing that they do is this. They end up factoring out LK from both these terms, okay? Now, they called it the distribution property. It's actually the distribution property in reverse. So we have JK squared plus LJ squared would equal LK, factored out, MK plus ML, okay? Now, from there, let's see here. LK. Oh, yeah. And again, this is the distribution property. Now, to finish this up, just so that we're thinking in terms of a proof here, here's what they did next. They have this whole segment, LK. And they said, you know what? LK is made up of ML and KM. So those two segments together are going to equal that entire segment right there. Again, that's the segment addition postulate. And to finish things off, let's see here. So JK, oh, I see what they did. So they have JK squared from that one that comes down. LJ squared comes down. And then they took this LK, since it's actually equal to MK plus ML, and they plugged it in right here. Well, what do you get when you get LK times LK? You get LK squared. And that then proves that leg squared plus leg squared will equal hypotenuse squared. Okay? So again, kind of walked you through the Pythagorean theorem there. All right, now let's take a look at the next one. I'm going to be honest with you, the first time I ever did this one, this is the part that got me. I didn't read that carefully, so just be aware. A map of Jamestown, a map of Jamestown with her home and workplace is shown. Jane wants to determine the shortest route from her home to her workplace. She walks only on the sidewalk indicated by the dotted lines. What is the distance of the shortest route to the nearest whole block? Okay. Now, I think there's two possibilities here. It could be this route here, okay, or it could be this route here that goes this way. Okay. Now, here's what I'm thinking. For this route right here, I'm going to change it into these right triangles here. If you look at those, that one and this one, okay? And I already know that this length here is a length of 3. This length here is a length of 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6, 7. And actually, since this length here will be the same for both routes, I don't even have to include that one, okay? If I can find this length here, let's say from A to B, okay, and also from C to D, I can add in the 1 and 1 right there for that one. So here's what I'm going to do. If we can get from here to D to B, if that length is going to be shorter than 13, then we know we want to take this route right here, okay? Which seems to me like the route you'd want to take, but let's just see. I'm going to sneeze. Excuse me. Whew. All right, so let's do this here. This length right here is 2. This length right here is 3, okay? So if I work that out, 2 squared plus 3 squared would equal CD squared, okay? So we're going to do 9 plus 4 is 13. The square root of 13 is CD. Remember? 9 plus 4, and then I want to square root that. And then I know that AB is going to be a length of, this is 2 right here, and this one is 1 right here. So we have a triangle that is 2 squared plus 1 squared would be the length of AB squared. So 4 plus 1 is 5. I'm going to square root that. That's AB. Okay. So to get there from the workplace, I'm going to go 3 plus the square root of 13. That's from C to D. Plus these 2 blocks right here. Plus the square root of 5. Okay. And we'll check and see what that is in just a second. And remember, if that's anything less than the 13 right here, 6 and 7, then we know that we have a faster route to get to the home place by taking that route that, again, to me looks like a shorter distance here, but we'll find out in a second. Okay? So, where am I going to go? I'm going to go back to Desmos here. I'm going to plug this in. Be gone, be gone, be gone. Okay. And let's do this. 3 plus the square root of 13. And then let's get you out of there. Plus 2 plus the square root of 5. So that's 10.8. That's less than 13. So therefore, I know what I want to take here. I want to take this route. I want to take this route right here, the one that we thought, okay? Now, here's the thing. I know what I want to take. Now I have to figure out this right here. What is the distance of the shortest route to the nearest whole block, okay? I didn't do that to the nearest whole block. What that translation is, nearest whole number. So I'm going to go ahead and do something like this. We already know what this length is up here. It was like 10.8. I'll go back to it in just a second. But what do I have to add in? Well, I have to add in that length that I said was irrelevant earlier because I forgot we had to get the whole length. So if I go back here, this length here is 2, and this length here is 1, 2, 3, 4. So with that last triangle, again, it's over 2 and up 4, over 4 and up 2. I'll label that BF. This is B, this is F, okay? So 2 squared plus 4 squared equals BF squared. 4 plus 16 is 20, and I'm going to square root that. That'll be BF, okay? So to finish this off, if I add in the square root of 20, that should give me my overall distance there. Now let's go back to Desmos here and do that. Plus square root of 20. Now you see this? Nearest block. What do you think I'm going to put? Nearest block would be 15 blocks. Okay? So it's approximately 15 blocks from home to the workplace here. 15 blocks. Okay. All right, now, for the next one, it says this: angle A and angle B are the complements of each other. Now, what is the complement? It means that angle A plus angle B equals 90 degrees. Okay. Now, does it matter which angles we're looking at? No. Okay. Which equation about the two angles must be true? Okay. Now, here's what I'm thinking. Let's plug this into Desmos and see which ones this will be. Now, what I would do before I start this is I would probably start by saying angle A is a certain value and angle B is a certain value. Okay. So let's just make this 70 and 20. Okay. Now I know what the answer is, and I can do this in several different ways, but let's just see if Desmos will solve this for us so we don't have to worry about it. Okay. And then I'll show you maybe how else you can go about solving this problem. So when I look at this, throwing this into Desmos, first thing I'm going to do is make sure I'm in degree mode. So if you go over here, I'm in degree mode. I want to do that first. Okay. Now the first one said the sine of A, maybe trig functions, there we go. I'll go over here to functions. The sine of A, which was 70 degrees, okay, is that right there. And is that equal the sine of B? Now B was 20 degrees. Oh, go back to functions maybe. Functions sine of, oh no, I don't go all the way back. Functions sine of 20. Okay, those are not equal. Okay, so the second one says the sine of A and the cosine of A. So I'll go to cosine of 70. And if you look there, they're not equal. Okay. So the third one, letter C, says the cosine of B and the sine of B. So the sine of B would be 20. And the cosine of B would be 20. Ooh, no, they're not good. How about the cosine of A and the sine of B? The cosine of A was 70. The sine of B was 20. Ah, they're the exact same. Now, I was kind of hoping that they would show a graph here, but it doesn't look like they do. Okay? So, not a big deal. Just know that you can plug it into your calculator until you get the exact answer out. Now, what I wanted to show you was this. As I look down here, and hopefully you could see that okay. I don't know if that was zoomed in enough. Plug those values into Desmos there, and I think it'll show you to you well enough. So yeah, we just determined this was the correct answer here. Here's something you could also do, is actually formulate a 3, 4, 5 right triangle, or any right triangle, just as long as you have the correct measurements here. And I'm going to put down A and B. Okay, now watch this. If I go ahead and do the sine of A, well, the sine of A is 4 over 5. And if I'm looking at this very first one, the sine of B would be 3 over 5. Remember, opposite over hypotenuse. Those aren't the same, okay? So now I'll go to the sine of A and cosine of A. The sine of A, as we said, was 4 over 5. The cosine of A is going to be 3 over 5. Adjacent over hypotenuse, okay? So those aren't the same. Now let's go down here to the last one where we knew it was the same. This was the cosine of A. I've got 3/5 right here. And we have the sine of B. So if I go to the sine of B, opposite over hypotenuse, it's also 3/5. So again, you can actually prove it without Desmos, but you know, Desmos makes it real simple. If you just plug it in, it should be a direct output from there. Okay? All right, folks, we're almost done. One last one. All right. So in this very last one, here's what it says. Which triangle must be similar to triangle XYZ. Now, remember, what do we know about similar triangles? Their corresponding angles are congruent, and their corresponding sides are proportional, okay? So as I look at this, when it says a triangle with two angles that measure 40 degrees, well, I got one that measures 40 degrees. Let's see if what the other angle measurement is going to be. Remember, the sum of the interior angles is 180. If I take 140 away from that, 140 from 180 gives me 40 degrees. This other angle has to be 40 degrees. So I'm thinking, yeah, that is the answer there. Okay. Now, if I go to B, a triangle with the angle measurements of 40 and 60 degrees, that's not the case, because while the 40 degrees does match up with one of the angles, this does not match up with any of the other angles. So again, the corresponding angles have to be congruent. A scalene triangle with only one angle that measures 100 degrees. Now remember, scalene means all the sides are of different length. Okay? That's not what we have here, because remember, when we have two angles that are congruent, what else do we know? Well, we know that the sides opposite those angles have to be congruent. So this is actually an isosceles triangle. The last one says an isosceles triangle with only one angle measure that's 40. Well, while we do have an isosceles triangle, we have two angle measures that are 40 degrees. Okay? All right. Now, I realize that was a long video. I hope you got something from it. I hope that you understood stuff. What I want you to do then is go ahead and do the homework for Monday that I've titled Monday's homework. Get that done for me. We'll come into class tomorrow. We'll submit our answers, and we'll go from there. So anyways, thank you for your time. I hope this is beneficial come next week. Talk to you later. Bye.